Welcome to session T7 of the 2025 Regulatory Information Conference entitled The Future of Fusion Power on the Grid, Building a Flexible, Resilient Regulatory Framework for Commercial Deployment of Fusion Machines. My name is David Wright, and I'm the chairman here at the United States Nuclear Regulatory Commission. Before we get started this afternoon, I've been asked to give you some ground rules and explain how we can all make this a great interactive panel session. First, the Wi-Fi code for attendees is RIC 2025, capital R, capital I, capital C 2025. Next, please remember to silence your electronic devices. The Q&A portion of this session will be through electronic means for both the virtual and the in-person attendees. For those of you in the session room, you may have already scanned or the QR code from the displays in the foyer, but if not, please take a moment and scan the QR code on the screen. If it is put up, there you go. You'll then be redirected to a specific session page for Q&A. If this is your first time today that you are accessing this Q&A, you'll need to log into the platform using the name and email you provided when you registered for the RIC. And this is only required one time a day, okay? For those of you joining virtually, once you've logged on to the virtual conference platform and joined the session, there is a tab for electronic Q&A. Questions from both the online participants and those using the QR code will be added to the same queue, which will be going right over here. And we'll try to get through as many questions as we can in the hour and a half we've been given for today's panel. This session will have 5 live polling questions. For those of you in the room, the slide showing the poll will include instructions for participants to text their responses. In-person participants will text the code next to their choice or answer to the numbers 22333. For those of you participating virtually, once you've logged into the virtual conference platform and joined the session, there is a tab for polls. Responses from in-person, and that's the same page again. I don't know why I want to read it again. So at the end of the session, if you have follow-up questions for any of the panelists, they'll be available at the front of the room, and I'm sure they'll answer your questions for as long as they have to stand here. And finally, your feedback is important to us. Please let us know what you thought about the RIC this year. Your insights are going to help us begin to shape next year's program. And you can provide feedback through the platform by selecting feedback, the tab in that session, or by accessing the link from the RIC website. Now, back to the main event, today's panel, session T7, the future of fusion power on the grid, building a flexible, resilient regulatory framework of fusion machines. To kick things off, my panel members and I would like to know a little about you, our audience. So we have a live polling question that I would ask Madam Producer if you would put up on the screen now. It'd be kind of like a test, okay, for you. For in-person participants, you're going to be able to text your responses, and the information provided will appear, as you can tell, on the screen. So please take a moment and vote. And Madam Producer, if you just leave the question up and let it populate until I ask you to take it down. In the meantime, I'm going to briefly thank a few people. I want to take a moment to thank Duncan White, who's going to be one of the panelists today, Ed Harvey, over here, Elise Bolger, where is she? Is she here today? For the time and effort that they put into making this session a very special one and packed it full of information. I'd also like to thank my staff, Team Wright, for their help and attention to detail on this panel, as well as in support of the plenary session where I gave my RIC remarks earlier today. So, based on the slide, there are a lot of government people here. I mean, it's more than 2 to 1 over industry. That's wild. Wow, that's good. So, Madam Producer, thank you. You may take the first question down. So, that's really good information right there. Today's panel is going to focus on efforts to generate the first fusion electrons to reach the commercial energy grid. The future, believe it or not, is happening now. It's not 10 years away anymore. It's now. And the panelists are going to discuss a number of the current examples demonstrating the immense progress that's been made in developing fusion technology as a means for commercial power production while ensuring its safe use through a flexible and efficient regulatory framework. This session features both fusion industry and regulatory agency perspectives on the development of novel, first-of-a-kind commercial fusion machines, efforts to scale production of fusion machines, and international harmonization of regulatory approaches to safely and efficiently license fusion machines. We have an awesome group of presenters on the panel today, and I believe you'll learn a great deal from each of them as we address this topic. To maximize our time for the topic today, I'm just going to give you a brief introduction of each panelist, but I would encourage you to please visit the speakers pages of the RIC program and agenda to view their full bios. It's an impressive group of experts. Kicking off today will be Jennifer Ganton, Chief Global Affairs Officer for Commonwealth Fusion Systems. Jennifer will be discussing Commonwealth Fusion Systems' path to deliver fusion energy, including their commercial demonstration project, SPARC, their first-of-a-kind grid-scale fusion power plant, ARC, and the importance of regulatory certainty. Next, we're going to hear from Andrew Proffitt, Regulatory Policy Lead for Helion Energy, and he'll be given a presentation on Helion's approach to fusion energy and their perspective on efforts required to achieve scaled deployment of commercial fusion technology. Following Andrew will be Duncan White, the legend, senior health physicist in the NRC's Office of Nuclear Material Safety and Safeguards, and he will be giving a presentation on the NRC's efforts in developing a regulatory framework for fusion machines, also the ADVANCE Act and the NRC's vision and strategy for regulating fusion machines across the National Materials Program. Duncan will be followed by Dr. Patrick White, Research Director for the Nuclear Innovation Alliance. Dr. White will provide his perspectives on the evolution of regulatory needs as fusion technology progresses toward commercialization and harmonization of fusion energy regulation on an international scale. After the panelists present, we'll have time for Q&A. For those of you in the room, again, please scan the QR code displayed on the screen. The code will bring you to that page to this specific session, and we'll have a tab for Q&A where you can input your question on your mobile device. For those joining virtually, again, click on the Q&A tab, and you can submit your questions through the browser. We'll try to answer, again, as many as we can get to, and I hope we can get to a lot. So please submit questions as you think of them. And with that, Jennifer, the floor is yours.
Great. I think we decided to do this from the table, so I'll go ahead and start. I also thank you, Chairman Wright, for inviting us today to talk about this. It's really meaningful to be here and have this event. And in the vein of the plenary this morning, I thought I would also just share a bit about myself. Since I started my career, I've been absolutely fascinated with energy and how companies can supply affordable and reliable energy to everyone around the world so they can achieve their greatest potential. But I'm fairly new to the RIC compared to most people here. I only came into the industry recently after 20 years in oil and gas sector, where I worked around the world building new projects and also spent about 8 years in Washington, D.C. on oil and gas issues. I joined Commonwealth Fusion Systems in 2021 because I saw a company that was developing a new energy technology that I think has the opportunity to change the future of our energy landscape in a profound way. It's been an amazing experience to build not just a new company, but a new industry. When I started, very few people had ever heard of fusion that I talked to and told them what I was doing. That has changed significantly too over these last few years as the technology has advanced, and we now have 40 private fusion companies, or more than that actually, globally looking to develop commercial fusion. It really feels like fusion's having a moment. My role is to lead community and government relations. That goes from local, state, federal to working internationally with governments on fusion policy and regulation. And I also lead an open innovation team that does the R&D partnerships around the world on fusion R&D with national labs and universities. I'm super fortunate to have a great team that has a depth of experience in nuclear regulations that is supporting the efforts that we're doing. And afterwards, grab me for a drink. I have a similar story to Commissioner Caputo, but mine did not end as well. So happy to share. Happy to share the neck brace I wore for 6 months. But I'm going to start talking about the importance of regulatory certainty first. I'll spend a little bit of time there, and then I'm going to quickly run through what Commonwealth Fusion Systems is doing and our timelines, and happy to answer questions during Q&A on that. So let's see if this works. We'll go here. Okay. So with respect to regulatory certainty, CFS has really prioritized this work over the past 5 years, despite we haven't even had a commercializable demonstration yet, right? We're still working towards that. It's because regulatory certainty is really crucial for fusion commercial development. With regulatory certainty, investors have confidence in the projects, and that helps us move through to finalizing designs, checks get written, steel gets bent, concrete gets poured, these projects actually happen. So this certainty is intrinsically linked with the investment decisions and the certainty of timelines and execution that we're working towards. The regulatory certainty that is developing in the US and the UK and elsewhere around the world is also establishing that sort of pathway for commercial fusion. We have been extremely appreciative of the work and attention of the NRC and the time that people have devoted to this topic over the past few years. We see the regulatory space as a real opportunity for the US to lead in fusion and really spur projects here at home to be built. In particular, I'd like to commend the NRC staff for their openness and engagement with the Fusion Industry Association and other stakeholders in this process. The staff has really run what I would call an admirable, robust stakeholder engagement process, including advanced publications like the preliminary draft guidance and so many other examples I can cite. The work is still ongoing as the NRC moves to complete the limited rulemaking and the guidance that's going to enable the building of these fusion power plants and the licensing here in the United States. But we do think this heightened engagement is going to really result in durable regulatory frameworks that are going to ensure safe and effective deployment of commercial fusion for the American people. So, why is certainty important? The deep level of engagement by the NRC staff and the commissioners and the expanding engagement with the agreement states that's now happening has allowed industry to provide important insights based on current demonstration machines and rapidly evolving designs for fusion power plants that we're all working on today that will ensure the important efficiencies that Chairman Wright and the other commissioners referenced earlier today in the plenary sessions. With respect to ongoing limited rulemaking, industry has provided feedback. We think it's very important that the NRC ensures the rulemaking language is consistent with the federal law and the guidance and the commissioner's decision last year that defines fusion machines as particle accelerators. The open engagement process as well has really helped provide guidance from industry into the rulemaking and the guidance. And the industry is pursuing a number of technology solutions. There's no one fusion machine. There's going to be various approaches to this. But we've been able to come together collectively through the Fusion Industry Association and provide direct guidance on things such as New Reg 1556, Volume 22, which is going to be how we move forward with commercial fusion in the future. So we think about things like not adding considerable licensing length that aren't associated with safety benefits. And some of this is thinking about environmental reporting and the licensing application, timeframes being ahead of when construction is, and industries willing to go at risk with construction. So really decoupling those things will be important so that we can move forward as fast as possible with construction, but that we ensure we have our licenses when materials arrive on site and we want to operate. No need for emergency backup power. We have to think a lot about what applies for fission and maybe what wouldn't apply for fusion. And so the fusion systems themselves are designed to not be capable of operating and automatically isolate in a scenario, so that we have to think about those things differently. So those are good conversations that we've been having with the staff. Other ones include tritium, if we think about inventory assessment. is an ability to do that through the fusion loop, and that's important, but we also want to think about safety first and the hazard for the workers. And so we think about that from, it's impractical to do it for everything. And so for activated materials, we're recommending more a bounding calculation, showing the maximum authorized level would be more appropriate approach for that type of thing. And lastly, we've had a lot of discussion. We're moving forward as an industry to ensure that volume 22 applies to commercial fusion machines and that the things that are in there are appropriate and able to move us forward as an organization. And this was probably not something that would apply to fusion R&D machines or things that are already under consideration, like Spark, which we're building. So the industry also supports efforts to assist agreement states in preparing for power plants. This could entail providing fusion education and training resources for the agreement states, but also encouraging the use of what we all call third-party staff augmentation, where that's paid for by the applicant, but it can be a very cost-effective and time-effective way of getting agreement state expertise that is needed to review the applications, and it's what we did with our agreement state in Massachusetts in order to license Spark. It was very effective. So it's crucial that we get this work done. A number of fusion companies are going to be filing applications in the next few years, and a large percent of the fusion companies have indicated in a recent Fusion Industry Association survey that they anticipate power on the grid in the early 2030s. So now it's really the time to sort of close this out and make sure we're ready for this industry. We also recognize the relevance of the ongoing discussions for more long-term regulatory efficiencies. We don't want that to slow down the current process, so we want to finalize the rulemaking and get the guidance out. But we think there's some good examples if we look to like irradiators or well loggers or other things like that, where we recognize that over time, we're also going to be able to take experience with construction operation maintenance and put in these regulatory efficiencies. But we got to get the industry off the ground first. So really exciting work to do. And I don't think I can say it enough of reiterating the thanks for the openness and the transparency and the process that NRC has brought to this. So I'll pivot now to tell you a little bit about CFS, and I'll try to go fast through this and be happy to answer questions more to make sure my other panelists have plenty of time. So we were founded in 2018, spun out of MIT. We've raised more than $2 billion in capital since that time. We've built, and that's really a diverse cap table, which includes venture capital, energy companies, pensions, endowments. It's really phenomenal that Fusion's been able to attract the attention of a lot of different sectors. And we've also built a diverse team. We now have over 1,000 employees, the majority of which who work in Devens, Massachusetts. And again, a real diversity of employees, people from tough tech startups to large industrials, to people with fusion expertise. So it's been an exciting time to watch this growth happen in this short period of time. So what's our path? We're taking a stepwise approach to addressing the key risks of bringing fusion power to the grid. Many of those are technical risks, learning how to build and operate things, but some are not technical, and that includes things like regulatory treatment of materials these fusion machines will use. We've completed some of the key technical milestones, and you'll see here they're in green. We've published our physics basis and had that peer reviewed, and the world has kind of said, hey, if you can get the magnets to work and some other things, this technology will work. We then went and did a demonstration of our magnet technology. So de-risking some of that technology has happened. And then today, we're now in the phase of, we're building Spark. Spark is the demonstration fusion machine the chairman referred to that's under construction in Devens, Massachusetts. It's about an hour outside of Boston. We've received our material license for 10 grams of tritium and activated materials from the Commonwealth of Massachusetts last fall of 24. And I would say securing this license, and more importantly, understanding what was necessary to get the license, retired a significant key risk for us as well that is not a technical risk. These are things that are important that we're doing as we go along. And so, again, the NRC played a very important role here, and we really appreciate the NRC's background assistance to Massachusetts and the partnership that they developed with Massachusetts to kind of achieve this first-of-a-kind license there. So next is ARC. That's the commercial power plant that you see there, the drawing of the commercial power plant. This will be our first commercial fusion power plant that puts watts on the grid, and we're anticipating that in the early 2030s. It will leverage a lot of the Spark design, but we're doing the remaining design work now is active and underway. I'll go through these. Wanted to share some pictures of what's happening in Devens. So here's a recent picture. A lot has happened since you visited us last year, Chairman, right? But on the left is our cryo system building. If the picture all the way on the left, there's a big wing where the cryo systems sit. In the back is our power building. On the right is utility and the RF heating that's going to heat the plasma. On the front is the diagnostics building, and the tokamak hall is the tall cement square in the center where the tokamak will actually sit. On the right, you can see we've moved in equipment, which is installation tooling. The base of the tokamak has arrived, and the magnets will be moving over into this installation system here soon. So it's starting to come together, the tokamak as well. We expect first plasma from this machine in 2026, and we're going to ramp it up after that, and it'll go to Q greater than 1 to show net energy gain. Not too long after that, likely 2027. So we're also manufacturing on this site. So we manufacture the magnets that are going to go into Spark, and we will also manufacture the magnets that will go into ARC, our power plant. And so the manufacturing building is on the same campus. It's been built up. And I would have to say that regulatory certainty has been key in supporting this kind of upstream investment in supply chain and technology development that we had to do, as well as that investment that our suppliers had to do. We are purchasing an awful lot of equipment to go into this building, and it really, people making the capital investment and going along the way with us in the supply chain really was catalyzed by them knowing that eventually we would get licensed and be able to turn the machine on through the regulatory certainty that's happened. So this regulatory certainty has a catalytic effect that goes beyond just our company. It goes all the way into the supply chain, which is really important. And so last but not least, I'll talk a little bit about ARC. So this is a rendering of ARC. It will be a net 400 megawatt electric power plant, putting watts into the grid, connected into the power grid. We recently announced the location of our fusion power plant. We did that at the end of last year in December. We did a multi-year search. But what was interesting was, as we started to think about where the first fusion power plant could go, we were limited to the US and the UK. It started as the UK in the early days, and it became the US when the Commission made the decision that we would be regulated under Part 30. The moment we had that regulatory certainty, it opened the market here in the US for us to say, we can now move forward with looking at sites here in the US. So we looked at a lot, hundreds. We ultimately down-selected to a site in Virginia. It had a lot of the key attributes that we needed, power requirements, siting, government and community support was really strong. We also had really positive engagements with the radiological health team in Virginia, and we continue to do that work. And they've actually staffed up their team as soon as we announced ARC. So great partnership happening there. So a really exciting opportunity for us to move forward with our fusion power plant there. So we anticipate beginning construction in 2027, late 2027, 28. That's the date we're putting out there. So as you can see, why I keep stressing the urgency of finalizing the rulemaking and guidance on time is because we will need to think about our application for a license fairly soon. I'll conclude there with, I think it's an exciting time, and we look forward to continuing to work with the NRC on these important things. And I'll show you one last piece, which I'm not even going to talk to. This is what a future power plant in the fusion sector looks like. If you can't imagine, what would this look like in my backyard? This is a rendering of the actual plant that will go into Chesterfield County, Virginia. I'll leave it at there. Thank you again.
Thank you. Thank you, Jennifer. So I already know this, but you are a busy lady, and I don't have to tell you that people here and around the world are watching what is happening at Commonwealth. As you guys reach out to meet the moment, right? So before we move on to our next panelist, let's bring up the second live polling question, Madam Producer. And this one is, when do you think the first fusion energy electrons will enter the U.S. power grid? So just leave this up while the results are populating. Okay, so most people think it's going to be somewhere between, most people are saying it's going to be 2040. You'll beat that. don't you think? So, and quite honestly, it looks like as you address the rest of you, if you want to address any of these slides in your remarks, please do so. Especially when we get to the Q&A part. Thank you, Madam Producer. You may take this down. Kind of split now between 20, 30, 35, and 20, 35, and 40. Yeah.
I'm going to say if you cumulatively add the 2030.
Yeah, that's good. All right, Andrew, let's hear about the initiatives that are happening right now at Helion. You can take it from here.
Thank you, Chairman Wright. Yeah, I really appreciate you inviting us here to speak, and what a time for your chairmanship now with Fusion coming ideally in the next few years, in your strong background and support with the agreement states. I know you've been a long supporter, been to every Organization of Agreement State meeting going back several years.
Since I got here.
And so I know they're really excited to have you in this position as they're preparing to regulate Fusion. So yeah, building off of Jennifer's remarks, certainly regulatory certainty and clarity is key for Helion as well. But to not duplicate her effort, I'll talk a little bit more about scaled deployment and what's going on in that regard, and how that is an opportunity for Fusion to meet the growing demand that we have, and some improvements or augmentations we see that could be done to the regulatory framework to enable that, and why we should start thinking about that now, so that we can get to that point. So I'm Andrew Prava, Regulatory Policy Lead at Helion. I've got over 15 years of regulatory experience, much of that in new or novel technologies, with the past few years being in Fusion in a really exciting space, especially moving off of the NRC's and Commission's decision, the Advance Act, to regulate Fusion differently from fission. So our mission here is to fully satisfy the world's need for clean, abundant energy. And I think we've heard that a lot, that affordable and reliable today that the U.S. needs and really the world needs. And so at Helion, that is what we're working to do. We're very mission driven, and our goal in there is to build the world's first fusion power plant here over the next several years. And so I'll tell you a little bit about what we're doing in that regard. So Helion's been around over 10 years now, and we've been building and doing fusion that whole time. We've built over 6 working fusion machines that have retired certain risks for us along the way, proved parts of our concepts, similar to Jennifer's graphic on the magnets and the physics. And the regulatory framework enables that. We've got over 450 team members now in Everett, Washington, just up from Seattle, in a great area of tech and manufacturing and technology and infrastructure. Really great team that we have there, and most of those folks are not plasma physicists or PhDs. They're folks building hardware and machines, and I think that's what's really different about fusion now versus maybe what it was over the past 10, 20 years ago, is right now what you have private dollars and commercial companies that are building actual hardware and machines to show that their concepts work. And so what we've been able to do over that time is in 2021, our last fusion machine, Trenta, demonstrated commercially relevant fusion conditions, 100 million degrees Celsius. And what that enabled us to do is gain significant funding and move us to where we are now, and working towards commercialization, and really build out a significant campus of manufacturing and testing capabilities. And also what we've been able to demonstrate over the past few years has enabled us to, what we're really proud of is securing customers in Microsoft and Nucor. We signed a power purchase agreement with Microsoft to deliver 50 megawatts of electricity in 2028, so a little before most folks' answers to the last poll. But that power plant is slated to come online in 2028 and then ramp up over the next year and get to a full 50 megawatts of electricity, and we're working on that. I'll tell you a bit more about that in Washington State as we're going through. And then soon after, we have an agreement with Nucor Steel, North America's largest steel producer, to deploy a 500 megawatt power plant at one of their facilities. And these are just great partnerships that we have, and two, very different customers. One being more the data center and AI-driven need, and then the other onshoring and reshoring industry into this country with clean energy to power it. So another way to really drive economic prosperity and jobs. So I'll tell you a little bit about Helion's approach. So we don't view it as a fundamental physics problem. We really see it as an engineering problem that we can solve through building, testing, iterating, and that's what we've been doing over the past 10 years and what we're continuing to do today. And so some of the keys about our technology is it's a pulse system. This takes care of one of the crucial physics challenges with fusion, which is confining that hot dense plasma for a long enough period of time. So this pulsing really lets us sort of shortcut that difficulty in meeting that moment there. And then also what the pulse system also lets us do is lets us ramp up and down in power. And this is something that's really important to some customers, not as much the data centers, but some of our other customers that we talk to are really looking for power that can go up and down. Also with renewables, peaking at certain portions of the day, something that can go up and down is really helpful for the grid. We also at Helion use an alternative fuel cycle. We use deuterium helium-3. And so this allows us to build a little bit more compact, efficient systems, being lower number of neutrons that come out of the deuterium helium-3. Actually, none from the deuterium helium-3, but the deuterium and deuterium will fuse when you're seeking deuterium helium-3 fusion, and you will get some neutrons out of that. But those are also lower energy neutrons than what you see out of DT. So it really lessens the hill there on the materials challenges that we need to work through as we get towards commercialization. And then the last piece of that, which really builds off that deuterium helium-3 fuel cycle, is direct energy recovery. So because of most of the energy coming off a deuterium helium-3 reaction being in charged particles as opposed to neutrons, you can directly capture that through its interaction with the magnetic field. It's the same thing if you have an electric car and the regenerative braking in your electric car does the same phenomenon there. And so not having a steam cycle lets you be far more efficient and also increase your flexibility and potential siting. You can see there that top building is where we're building Polaris today, the fusion machine we're building right now that is expected to show electricity production from fusion. You can see it's in a light industrial area in Everett, Washington. They're not too far from neighborhoods. Some of our direct neighbors are coffee roasters and equipment rentals, and so nothing too exciting about the site there. So this is an overview of what our process looks like. You'll see this symmetric fusion generator here that we have, and I'll play the concept here. You'll see we puff in on both ends some deuterium and helium-3 gas, create a field reverse configuration of plasma there, pulse the system, move those two plasma donuts to the center through well-choreographed dance of those electromagnets. Really squeeze it tight in the middle, get to those fusion conditions. That plasma starts to expand, push back on the magnetic field that you squeezed it with, and you end up with more electricity back on your power bank than what you started with. And you just do this over and over again, and actually in a non-ignition way. Being the pulse system, we don't need to reach ignition conditions to be commercially viable here. And the other thing here that's really key is you have a very, very small active amount of fuel at any given time. Now what we're putting in is deuterium and helium-3, both stable isotopes, not radioactive at all. But what we do get from our deuterium fusions is sometimes you'll get neutrons and sometimes you will get tritium. So you will have activated materials and you will have some small amount of tritium, but we're talking fractions of a milligram of tritium in each pulse here. So really small amounts of active radioactive material in your system at any given time. And here I've got this little bottle here of deuterium, and this is a gram of deuterium equal to 10 tons of coal in energy and could power your home for a year. And this amount is actually in everyone's body right now today with how abundant deuterium is out there in our world. So really a very energy dense system here. So where are we today? What we're commissioning Polaris. We're doing our final integration in our commissioning test for Polaris. It's our 7th generation machine. We consider it our pre-production generator because it really is, its purpose is demonstrating that electricity production from fusion energy, turning fusion energy into electricity. And what that'll do is it'll demonstrate the end-to-end architecture that we're looking at for a power plant. And so we're looking to ramp up its commissioning and operations over this year, and really excited for what the future holds with Polaris, sort of putting together those past 6 machines and taking them to a higher scale with showing electricity production. And we're regulated by the Washington State Department of Health. We've had a long relationship with them, coming up, I think, on 5 years almost now, and has really just been a great partnership where we've grown with them, starting with just licensing some sealed sources, all the way up to having several grams of tritium in our license and the activated material that we need to operate Polaris. And that has been such a great partnership with quick turnarounds, open dialogue and communication, and has really been a real key enabler for us in moving forward with our concept here. So here's some of what's in that building today. In the top left, you'll see some of the racking where all those capacitor pallets that you see in the top right and bottom left will be going in and are filling up very quickly as we speak. I'm sure all those racks now are full, but all that cabling, over 1,000 miles of cabling for this machine, and even more for a commercial machine. Putting together those pallets, I'll talk through a little bit more in a couple slides. And then the bottom right, some of our magnet segments, which are all pretty small things. None of them really any bigger than this table here. So all pretty compact things. And once you put them all together, they get a little bit bigger. But really, it is a fabrication and assembly of manufactured components, I'd say. This is Polaris, the end of last year, our first plasma in that system toward the end of last year in one of the sections. So really excited to have sort of that first initial test done and have made plasma in the machine and given us confidence to move forward and complete integration and start ramping up our testing. So that brings us, to our next step, which is building that first fusion power plant, needing that certainty in the NRC's rulemaking and guidance to move forward positively to really enable this. And we're working through siting in Washington State right now to deliver on that Microsoft Power purchase agreement. And as you can imagine, to deliver electrons in 2028, one of the real drivers for that is a grid interconnection. I'm sure most of the folks in this room know how difficult that is at this given time. So that does narrow us down, but we have targeted several options in the state and engaging those communities. Really the most important part, more so than the grid interconnection, is having that community support and coming in somewhere that's excited about fusion and wants to be home to the first fusion power plant. So a lot of exciting work going on in Washington State. And then outside of that, we'll be moving towards Nucor, a 500 megawatt facility, and then quickly to scale in the 2030s. And so how will we sort of be able to do that? Really, fusion can be a mass manufactured product. I think we've heard that a bit in the nuclear field, and it hasn't quite come to fruition, although I think a lot of steps are being taken on the fission side of the house. But in fusion, it really can be. There's no license needed to make any of these components. There's no radioactive material needed to make any of these components. Largely electric systems, like building a really big computer almost. I mean, building these large capacitors, assembling them together with technicians. All this stuff can be done in a factory and largely put together and shipped to a site being of a modest size. And then the other thing it's really key is just the low site work that you need for deploying one of these facilities. So similar to maybe LNG or some of the other power facilities that are being deployed today. Something that's manufactured and assembled in a factory and then shipped to site and quickly integrated with the grid there. So the NRC has been tasked with looking at a framework in the ADVANCE Act, maybe one of the lesser known aspects of the ADVANCE Act, but was looking at a framework for risk and performance-based licensing frameworks that can enable the deployment of mass manufactured fusion machines. And we really see, as fusion is proven, that the demand is obviously there. This unique siting capability and other aspects really will have quite the market for fusion. And so we think that now is the right time to start considering what the regulatory framework could look like, given the time that it takes to do that. And so what you see in this slide here, one of the things, Helion, we've put out a paper, just updated it this past week, looking at what kind of concepts could work for fusion. And we looked at concepts within the NRC, but also outside of the NRC, and where really society demands us regulators be able to meet the moment for critical technologies, and certainly energy is one of them, and will only rise over the coming years. But if you look at airplane manufacturer, the FAA, over one new commercial aircraft is produced every day in this country, and several million, 3 million people or so fly every day, 1% of the population. This is done extremely safely with their framework, and it's largely based on a initial review of the design, ensuring the operator, the airline, can maintain and operate that equipment safely and within its design requirements, and then oversight of the maintenance and deployment there. If you look at transportation, if you look at motor vehicles, over 16 million new cars were bought last year in 2024, and the American public has driven billions of miles, with over 90% of people over 16 driving at least semi-regularly. So again, a concept that actually with the car design, it's a self-certification by the manufacturer. It actually doesn't involve the regulator approving each concept. The regulations are put forward and the requirements are put forward, and the manufacturer certifies that they have met that, and then oversight and inspection can be done to ensure it. And then licensing is done by the states. It's maybe similar to what will be done in Fusion, and is enabled nationwide, and you can drive any car, outside of large commercial vehicles maybe, but any commercial car you can go out and drive if you're capable to do that anywhere in the country. And then also the medical field, obviously a critical technologies being deployed there, dozens each year being approved by the FDA to be implemented across the country for the betterment of our health and society. So what we see, our paper titled Preparing for At-Scale Deployment of Fusion Energy, looking at novel licensing pathways. Some of the things that we see here is addressing the limitations of the current framework that is really a bespoke site-by-site licensing framework that sort of starts from scratch in each new state that you would go to. So how can we make that more efficient? And so what we see is number one, looking at those core elements of those other processes. What we see there is really a risk-informed design approval, followed by that nationwide permission to operate. And then, really the NRC and agreement states bread and butter there, that robust continuous oversight. NRC has done very well in that regard, and the agreement states obviously a big part of their program is inspection and oversight. So looking at these three things, and then sort of the additional consideration for a fusion power plant is really that environmental potential review, right? If you're putting a significant infrastructure development in a community, that is something that needs to be done and will be done at the NRC under NEPA, and many states have similar SEPA requirements. So what we see there is there's three steps that the regulator could take. It could be the NRC, it could be the agreement state-led, but what could be done there is establishing a fusion generator registry, similar to another NRC concept, the sealed source and device registry, where really the regulatory requirements are assessed for that design. What you see in parts 20, parts 30 in the new reg that's being developed, those are all generically assessed upfront with that fusion generator registration. Having that license be for an entity, they would prove that they're technically and financially capable of operating this machine within that design, and then being able to deploy that nationwide is a real key, and that would be streamlined. It would focus on referencing that prior generator registration, and then really just proving that capability to do so safely. And then lastly, a streamlined environmental review process. And this could be done two ways. It could be done on a generator-specific basis when it's being registered, looking through the environmental report, but looking at a broad siting envelope. And there is precedent for this in NRC work with generic environmental impact statements. We don't think, based on the environmental impacts of the fusion machines so far, that they'll have large enough to warrant an EIS, but maybe a generic environmental assessment to look at that power plant with design within a siting envelope. Or even furthering that is going to a generic power plant design, looking at a technology-neutral fusion power plant parameter envelope and a broad siting envelope. And these are things we think should be started to look at now and documented in the NRC's report that they're working on as part of the Advance Act, and then we can work on how we implement these and have more conversation about each one as we go here. So this is sort of just the illustration in full concept in practice, but really what it is it leads you to that last step of where a licensee that has been verified by either the agreement states or the NRC is qualified to safely operate one of these machines to be able to do so nationwide. And that would really, I think, be key and really be what we need to truly unlock the ability for Fusion to scale and be deployed, and not get to a place where, would really be untenable of where, the industry can manufacture machines that could be powering the U.S. or the world, but not being able to be deployed. And we really think that, these things take years to do. I mean, even the current rulemaking, I think we're in at least 2 years in maybe, and that's a really straightforward and simple rulemaking, but again, a deliberate process and made that way for a reason, right? To make sure that we have all the appropriate conversations, bring in all the stakeholders. And so we're looking at the early 2030s for this scale deployment, and so we really think the time is ripe to start thinking about this now. So thank you.
Thank you. Thank you. Thank you, Andrew. That's very interesting, and I did go out there, saw it, and you talked about affordable, reliable energy. We also need it to be abundant, and a lot of people want it clean too. So you're hitting the marks there. So before we move on to our next panelist, let's bring up the third polling question, Madam Producer. Which milestone or accomplishment best indicates readiness for a specific regulatory framework or guidance to support mass manufactured fusion machines? It's probably a little bit more difficult question than what you were expecting. Let's give it a minute here to populate. So the first two presenters did a great job, but we've got 2 more to go. So get ready. So I'm curious here, where are we at? So right now we're looking like 57% are net positive sustained fusion. Is that right? That's going up 68. All right, very good. So thank you, Madam Producer. You can take that down. And so next up is Duncan White from the NRC. I'm excited to hear your perspective on regulatory approaches for fusion machines. Duncan, the floor is yours.
Well, thank you. Again, my name is Duncan White. I'm the technical lead for the fusion rulemaking, and I work with a great group of people at the NRC working on not only rulemaking, but some other activities which we're going to talk about now. One thing, I guess fusion is like a coming home for me. When I was a young HP back in a long time ago, I lived in central New Jersey most of my life, and I lived in the vicinity of Princeton Plasma Physics Lab, and they were building and testing this device called TFTR. It's probably the world's first, or one of the first, tokamaks that used deuterium tritium fuel. And I saw when it was being built, when it ran, and when it was being decommissioned. And I was away from fusion for a while, and beginning of this decade, I was pulled back into it. So I guess, all things come full circle. So I'm back in fusion. It's fascinating. A lot has changed since when I first got involved. So I think we're in for exciting times, and I'm glad that this opportunity today to talk to everyone. So at the NRC, people were talking about what we were doing with the rulemaking. We submitted this limited rulemaking to the Commission back in December. Limited means there's not much there. It talks about how to submit an application. It talks about something about waste because it's unique to because it's related to particle accelerators. There's talk about environmental reviews. Not much there. It takes up, probably 2 or 3 pages in a Federal Register notice. There's not a lot there. Important part of it is that it is a risk-informed, scalable approach, and that's because it's in Part 30. Again, the Commission had the foresight to put this in Part 30. The risk involved with fusion is comparable to larger byproduct material facilities regulated under Part 30. And it's, most importantly, it's a scalable system. And again, you heard from Andrew and from Jennifer what they're doing. There's also 23 other companies in the United States doing fusion right now, and some are doing fusion on very small scales that go on satellites, and some are building power plants like we heard a few minutes ago. So we have to have a regulatory structure that encompasses all these approaches. And again, our approach was to write a licensing guide. Again, our regulations talk about it on a broad scale, but the licensing guide is where we're going to get to the licensing and where we're going to get to the specifics. And that guide doesn't talk about tokamaks, doesn't talk about FRCs or inertial fusion, which are the laser types. It talks about how you're meeting requirements, how you're going to confine, shield, and contain radioactive material, because that's what NRC regulates. We're regulating radioactive material and the byproduct material that is produced by particle accelerators and as part of that fusion machines. And the regulatory structure is, again, is set up to do any type of scale. We had to write one guide that was a Big 10, and that's what we did. We published our first draft guide back in March, about a year ago. We have revised it. We've gotten additional feedback from industry, from the agreement states on what that's going to look like, and it's been changed. And we expect more changes. It will go out for public comment again when the rule is voted out. The Commission look forward to getting the Commission's SRM on that, and we will have an opportunity to publish it and have a formal public comment period. So we look forward to that happening. Another thing about the rule, and again, this goes back to the Advanced Act, which was passed last year. A lot of people have been talking about that. Section 205 of the Advanced Act did a couple of important things, and we incorporated the definition of fusion machine into the rulemaking. Fusion machine is a technology-neutral definition describes fusion in the first part, and the second part describes what it does directly. And I think that's important, because again, that type of definition serves well in the rulemaking space. It's not technology specific in any respect. The other thing it did, which was important, it said that fusion machines create byproduct material. It was put in the particle accelerators section. Particle accelerators produce rad material. Fusion machines produce rad material also. But again, the important thing is it says fusion creates byproduct material, and we can regulate it under the Act. Before, fusion does not show up anywhere in the Atomic Energy Act. Now it does, and we put that in the rule, and that's very important. It also, Section 205 of the Advanced Act also made some conforming changes to NEMA, the Nuclear Energy Innovation Modernization Act, which was passed in 2019. In that act, it's described fusion reactors. It replaced it with fusion machine. So this is why we call it fusion. We don't call them fusion reactors anymore. We call them fusion machines. So if you learn anything else today, that's the important thing. What I'll not talk about next is, again, what Andrew was talking about quite a bit was about the mass production of fusion machines and how we're going to do that and what the framework we're going to develop on that. Again, this is a tasking that was in the Advanced Act, and it asked for two things. It asked for a report to Congress on, to take a look at, the scope of this and make some recommendations on that. It also talked about the timeliness. When's a good time to deploy and do this? And I think that's equally as important, because we don't want to rush into this thing. We want to deploy it, and when we have an opportunity, when the industry gets close to doing that, we learn more. One thing that's very clear in this industry, and one thing when I quickly learned, is that there's a lot of work has been done, but a lot more work needs to be done. There's a lot of work needed with material effects, a lot of research going on in that area, and there's also a lot of work going on with regard to how do you turn this fusion energy into electrical power or to heat? How are you going to do that? And again, it's something that's that's going to be a challenge. And again, that has not been fully vetted out. And again, those things had to change. And as a regulator, how are we going to handle those things going forward? So for that reason, we need to be flexible and, keep our options somewhat open with regard to that. But getting back to the 205 report, again, we're looking at ways to approve a standardized license for a particular type of fusion machine so that design can be commercially deployed. They can, the company can produce several of these things and sell them to customers. So actually under Part 30, we do have a framework like that. It's, you see in Part 32, specific licensing. Again, we use this for a lot of different types of medical devices. Industrial devices is used quite commonly. Part 71 is for packaging rad material. Some byproduct material is particularly what's called Type B packages. Those are the packages that have to withstand, crashes and fires and, dropping from high heights and stuff. And some of the byproduct material has Part 71 approvals also. Those two processes are mainly internal type processes. There's no external components to that. But we're also looking at Part 72, which is the ones for ISFCs and other high-level waste. That process is, again, an approval certification process, but there's a rulemaking component to it, and there's also a component that's for public outreach. And so it's something, again, we're looking at and considering what's the best way to do this. The last one we listed there is nth of a kind, and this is a relatively new development. Looked at from microreactors, and it kind of harks back a little bit with what Andrew was talking about do we have can we come up with a certification type of process? And again, if you look at the nth of a kind paper and looked at the presentations they made, they talked about certified design, a manufacturing license, or some way that you did a robust review of the safety of the device. And again, since I said before, we regulate byproduct material. We want to make sure from our standpoint, is the fusion machine, is it robust enough to contain, and shield the radioactive material? So the nth of a kind is one of the interesting aspects of that is if you have a standard type of designs that you can deploy, can you put a box around that and says, well, if it's within this amount, you don't have to do an emergency plan. If it's this amount, don't you have to do a environmental review? Do you, certain things, aspects of that may be very useful to look at going forward. Again, a lot of work has to be done in that area, and I think that's, again, it's worth a look, and we're considering that along with some other things, again, that Andrew talked about. Again, is we were directed to talk to FAA. We also have you mentioned transportation, Andrew, that we talked to DOT a lot. FDA has some stuff. Agreement states have done some activities where they have, one agreement state licenses a certain type of medical device, which the rest of the NRC and other agreement state use. So there's different ways of doing this, and we're looking at all these and see, where there's some best fits there. We've also, engaged, part of the thing too is we've done a lot of other engagement too, not only with the Section 205, but we also engaged during the rulemaking. Not only we talked to the to our, the external stakeholders in industry in the states, but DOE has a very important role with fusion. Again, DOE is on the front end of this. They are promoting innovation. They're issuing grants, and they're working very hard to, to get, to push the fusion industry forward. And again, we talk to them a lot and compare notes a lot. The other thing that we're involved with is standards and codes. Is something that does not exist for fusion yet. Back in 2023, ASME did in fact issue a code, the first code, and it was based mainly on the ITER device, or the International Thermonuclear Experimental Reactor. And we're using that reactor term again, but again, ITER is it's an international. Many countries are involved with the building of that. It's a very large device, and ASME issued a code basically surrounding like that, but that's not what's being built today. What's being built is what you heard from Jennifer and Andrew, and there's a lot more other things being built. And what they're doing, what ASME is doing now is trying to look at the code and say, can we put together a code that kind of covers the breadth of what's being built. And it's more centered around, all the different types. You have metallic portions, you have non-metallic, you have ceramic, and there's other aspects that, that ASME can contribute to that, something we're following very carefully. So these are the engagement is wide-reaching and broad. And I think this leads to the next thing, which is as we move forward. Again, it doesn't end with rulemaking, it doesn't end with Section 205. Again, what we have to do as we move forward as a regulator has to ensure public confidence in what we're doing today and what we're going to be doing in the future. And we have this person who first manager who oversaw the fusion, Teresa Clark, had the foresight to start working on this, and we finally finished it up. We published it today. It's in Adams today, and we're going to put it on our website in the next couple of days to see this. But what we talk about here is, the fusion framework that enables a clear, efficient, independent, and reliable licensing and oversight through open processes. We follow the NRC principles of good regulations, and you can see it's under. It's broken down to three areas: regulatory optimization. And what we mean by that is, you heard from Andrew and Jennifer, is that they need consistency and certainty, but they also need flexibility, because again, they're building the devices. They're not commercially viable. They're seeing what works, doesn't work, doing a lot of testing. So they need that flexibility and also with that consistency. Technical readiness. As regulators, we have to grow with the development of fusion as the industry evolves. We need to be ready to regulate and be knowledgeable of the technology as it develops. And then in partnership and coordination, again, new things are going to be developed. I mentioned new things will be developed with regard to materials, things with regard to the fuel cycle part of it. We have to continue talking to industry, the states, to do all these things and get these things done. If you look at the document, it does lay out some things that we've been working on, some things that are coming up. And again, as I said, we look at this as a living document, and we look forward to again, making this document, updating as we go along, down the road. Again, look, this is a very dynamic area, and we need to change and innovate and be efficient as possible going forward, as a regulator, to keep up with industry. And the last thing, last slide here is I want to talk about, the importance of engagement, and I'm glad Jennifer and Andrew talked about this. Agreement states in this process have been invaluable. They've been regulating fusion for decades. All the R&D has been done in agreement states: New York, Wisconsin, California, and a number of other states. And the proposed rule, I think we had 7 public meetings, 6 government-to-government meetings with it over like a 14-month period. That was done on purpose. We deliberately want to engage industry, the states, in what we were doing. We floated some ideas out in the beginning. We heard, good, bad, and the ugly back on that thing, which was exactly what we should have heard. And again, we're working through all those things. And again, I think by doing this, we're going to end up with a good rule and something everyone can rally behind. And again, it's important for the agreement states, because agreement states, as being our partners, they will be also being regulators of this along with the NRC. So they need to be able to use this also. Section 205, again, states have been very involved with that. The states we have 3 people working on this Section 205 report. Going back to the proposed rule, we had the guidance document was, I think, half NRC, half agreement state people writing that document. Again, it was I think very proud of the people who did that. We got it done in like 4.5 months, which was very fast for a new reg guide such as that. But again, it was a good practice. Why we got people who worked on this stuff before we're actually regulating was good. The vision and strategy document is no different. That document's going to be a document that's going to enable us to, again, look forward and again, learn as we go forward. And then the last thing is, again, NRC has been active internationally. We were involved with the development of the fusion key elements, which is a cornerstone for what IEA has developed for fusion going forward. We've also been involved with meetings, develop of technical documents. We've been involved with the G7 as they stood up their fusion committee. But I think the most important thing, which I'll leave you with, is I think the most important international engagement the NRC has been involved with is meeting with the Canadians and with the United Kingdom. Again, both of those countries are approaching fusion in a similar way as the NRC is and the United States is, and we are able to share lessons learned, what challenges that we're going through. Again, Canada is very important because Canada has the largest commercial tritium industry in the world, and there's a lot to be learned from them. And we had an opportunity to go up and visit them last December. Again, very, very valuable. So I know that Patrick is going to talk about the international, so I will leave it with that and let him fill in everything else I missed there, and I'll turn it back over to the chairman.
Thank you, Duncan. Yeah, and I really want to thank you for all your work ensuring that the NRC and the National Materials Program remains agile and ready for regulating this particular technology. Before we go on to the last speaker real quick, I want to bring up the fourth polling question, Madam Producer. What do you see as the biggest barrier to the commercial deployment of fusion machines? This should be a pretty interesting question. We'll give it just a second here to start populating because I'm really curious to see what people think. Converting fusion energy output to electricity. That's interesting. That's what you got to do. Well, I think you will get there. So thank you, Madam Producer. You may take that down. And now, Dr. Patrick White from NIA. He's going to be the final presenter before we get to another question and then at the Q&A. So, Patrick, the floor is yours.
Great. Thanks so much, Mr. Chairman. So, like you said, my name is Patrick White. I'm the Research Director for the Nuclear Innovation Alliance, which is a nonprofit think tank really focused on creating the conditions for success for new nuclear technologies, really through a lot of technical advocacy and policy advocacy. Today I'll be speaking about a project that NIA has been working on in partnership with Clean Air Task Force to really start addressing how do we create those conditions for success for commercial fusion energy, both in the United States and around the world. And specifically, I lead the International Working Group on the regulation and licensing of commercial fusion technology. So today I'll share some thinking that we've done on how can we start enabling the global fusion energy deployment through harmonizable and scalable regulation. I think before I get started, the main takeaway is really over the course of the next 15 years, as we think about deploying commercial fusion energy technology, both in the US and around the world, we're faced at how we're going to regulate a variety of different technologies that may have changing regulatory requirements throughout their life cycle, and ultimately are going to have very different stages of development. The regulatory processes that are necessary and appropriate and reasonable for a scientific demonstration may look very different than that of an nth-of-a-kind technology. And how do we make sure we have a regulatory system that can efficiently and effectively accommodate all those different technologies? So from our perspective, it really comes down to this idea of how can we have proportional regulation that ultimately reflects the actual hazards posed by a technology to make sure we're regulating to an appropriate level of safety. How can we think about a harmonizable regulatory system that ultimately can be used across the world as opposed to having a fractured system of different national regulators? Even though they might not use the same exact set of regulations, how do we make sure that there are common themes? And finally, how do we talk about a scalable regulatory system? Something that we can ultimately use to deploy fusion energy at scale that we need to really meet global energy demand. And so with that, I'll just flag to start out a little bit some of the discussion of the CATF Fusion Safety and Regulation Working Group. And again, it really is this idea of how can we try to align the many different stakeholders that are going to be required to see the successful deployment of commercial fusion technology. And one of the challenges is really this idea of how do we address the varying regulatory needs of different technologies throughout the technology life cycle and at different stages of commercialization. And so I think to get started, it is just kind of good to give a little bit of context for everyone out in the audience. What makes these machines different? Up here, I've just put up 8 of, I'm sure now, the several dozen different commercial fusion energy companies that are developing technologies. And we see a variety of different factors that can affect the potential hazards posed by the technology and the safety systems that they'll use to ultimately ensure safe operation. We can talk about the confinement methods or fusion fuels, fusion fuel cycles, power conversion cycles, facility size. Even just for these 8 companies, there are no 2 identical designs that are being developed by commercial partners. And so I think if we take a look at this from a regulatory perspective, how are we trying to create a framework that can enable the efficient and, again, effective and predictable licensing of all the fusion technologies that are under development, just recognizing the myriad of amazing approaches that are currently being worked on. I think the next thing to really talk about is how we might think about the regulatory requirements will change throughout the lifetime of a fusion machine. Historically, we can think about everything from design up through siting, construction, commissioning, and operation, and ultimately how do we return the site back to a greenfield or whatever's the agreed upon site following completion of fusion power production. And there could be a lot of different regulatory requirements that occur throughout these steps. For different technologies, whether it's natural gas, wind, solar, fission, there are different technology requirements that might apply. And so it's remembering how can we make sure that there are appropriate requirements at these different life cycle stages. How can we think about the different regulatory authorities, the role of different permitting types, the need for regulation at life cycle stages, where is it needed versus where is it not needed, and maybe a regulatory approach can be stepped back because it's not relevant for that technology. And ultimately, how do we ensure the safety of workers, public, and the environment? And finally, as we talk about regulation, it's this idea of how the needs for fusion machines are going to evolve throughout the development and commercialization process. As we see companies move from their very first scientific demonstrations up through the development and deployment of technologies that are going to produce net power on the grid, the specific designs of the machines, the potential regulatory significant hazards, and the kind of scope of the regulatory process is going to change significantly. And so we need to make sure that we have regulatory systems that can really evolve over time based on the purpose, the hazards, the experience with the technology, and the industry maturity. Trying to create an nth-of-a-kind regulatory framework that is perfect in the long term might not serve the fusion industry well today as we're trying to really demonstrate and deploy these technologies quickly and efficiently. And so the question is, what does this future regulatory framework look like, and what are best principles to try to consider? And so one of the first ones that we'll really talk about is this idea of proportional performance-based licensing requirements that ultimately enable regulations to scale based on a specific application. One of the common hazards that's often talked about with some fusion technologies is the tritium as part of the deuterium-tritium fuel cycle. And one of the things that you find if you start looking out in the literature of companies that have looked at commercial or research facilities in the past, the commercial demonstrations that are underway today, and some proposed technologies, you can get orders of magnitude difference in what some of the potential tritium-related hazards are, just in terms of their on-site inventory. And so, if we take a look, historically when people talked about some of the large European machines, they might have had inventories of thousands or even several thousand grams of tritium on site. That looks very different than the scientific demonstrations that are underway by some of the companies today that might have 10 grams or less of tritium, and some of the proposed commercial machines that might be only in hundreds of grams. And how do we make sure that we ultimately have a regulatory system that allows the scalability of these different requirements based on the specific hazards? It's as you start to really think about what is required to provide that reasonable assurance of adequate protection, let's make sure that we have licensing analysis, the focus on engineered safety systems or operational safety, any type of emergency planning or environmental impact and review requirements really scaled based on that technology. What is appropriate for one machine might not be needed for another. And how do we make sure we have a regulatory system that allows for that type of flexibility? And I think like Duncan spoke to earlier, that is one of the ideas really of this Part 30 system for the initial framework is that provides that flexibility. And so in that way, I think we're definitely on the right path to think about this near-term fusion technology. I think as we start looking kind of broadly internationally, the question is, how do we think about harmonizable fusion regulation? One of the things that we see in many industries, it can be very hard to license a technology in one country and then deploy it in another. There are some industries where they've essentially created very strong international agreements on deployment of technology, aerospace, for example. But there are other technologies and other industries where they've had challenges in terms of coming up with uniform sets of regulatory requirements that allow for really easy cross-border deployment of technology. I think if we're really interested in fusion energy playing a major role, we need to talk about what are those regulatory principles that ultimately allow countries to determine the regulatory approaches that are appropriate in their country, but also maximize the opportunity to deploy this technology abroad. And a couple of major factors I'll just hit on. I think the first is just an understanding of what the kind of common safety requirements are going to be for deployment of fusion energy technology. How do we talk again about these proportional or scalable regulatory requirements? How do we enable kind of the adoption of international standards while still allowing national limits and ultimately recognizing the national sovereignty to determine what is safe technology in your country? I think when we talk about kind of developing the safety case or demonstrating the safety of your fusion machine, are there ways to enable or facilitate through industry agreements or through informal partnerships this idea of maybe standardized methods to analyze safety? Again, we don't necessarily want to prescribe what these methods are, but try to allow countries and companies to start to agree what are simple ways that they can say, yes, this is a good way to show the safety of a fusion machine that ultimately enables deployment. When we talk about licensing review, I think this is another place where really proportionality and scaling comes into play. How can we make sure that we're really scaling the amount of regulatory oversight and the amount of regulatory review based on the hazards of the technology and based on the safety case of the technology? And instead of starting with an extremely onerous regulatory system and say, let's chip it back for technologies that might be lower hazard, how can we really think about a bottom-up approach of saying what are the regulatory requirements that are ultimately going to be appropriate to help ensure safety and make sure that we're trying to really facilitate access to this technology? And finally, I think when we think about ongoing regulatory oversight, again, really thinking about how do we make this proportional? How can we create regulatory oversight that is proportional to the risks and hazards of the facility and make sure that we're not over-regulating technologies just because of perceptions around its risk or hazards? And really this idea of if we get national alignment on some of these kind of high-level principles, does that allow for the harmonized development of regulation on a national level moving forward? And finally, I think it comes down to this idea of scalability of fusion energy. It's that need that I think Jennifer spoke to earlier about having that regulatory certainty in the near term to make significant investments both on the Spark they're building today and the ARC that we hope to see them build in the near future. And then also start to provide that long-term predictability so we can think about the technology deployed at scale. So in the near term, again, try to really make sure we have that predictable licensing so companies understand what are going to be the requirements and what's the pathway. And then, as we think about developing more experience with the technology, start to address, hey, how can we think about updating the regulatory system based on lessons learned? Is it, for example, taking the types of machines that we're developing today and thinking about how we could use streamlined agreements or state licensing processes under Part 30 to really see fusion machines developed at scale? Is it something similar to what Andrew spoke about in terms of kind of the mass manufacturing, and how can we leverage some of the lessons learned from the ADVANCE Act and the work that Duncan and his colleagues are working on? Or if you start seeing fusion machines that maybe are looking different than the ones we're developing today, how do we go back and take a look at Part 30 and say, are there additional changes we might need to make if someone wants to build larger fusion machines or might have hazards that differ from the technologies that are currently under development? But it's really recognizing that these are questions to have down the road, but have an eye on ultimately how do we create that predictable, harmonizable, and scalable regulatory framework. And so I think just briefly, I think we are making progress around the world on this idea of harmonizable regulation, but we need to think about how we're ultimately going to implement that scalable regulation. It's not just about deploying 1 or 2 fusion machines, it's how we can deploy hundreds or thousands of fusion machines. And again, not just in the United States, but around the world. In countries that have used nuclear energy, but almost equally or more important in countries that haven't used fission energy in the past. How do we enable really global access to fusion technology? I think in the United States and in the UK, we've really seen kind of a lock-in on this idea of fusion technology regulated as radioactive materials. In France, with their experience on the ITER project, they're regulating it as a nuclear facility. And in other countries, we're still seeing these discussions underway. So I think there's a really strong opportunity here to see how can we try to align this work to ultimately create that pathway towards development of commercial energy, commercial fusion energy. And with that, Mr. Chairman, I'll hand it back to you.
Thank you so much, Patrick. Thank you, thank you. So, Patrick, thank you. I really enjoy the points that you made here. They're very important. But and Madam Producer, I'm going to forego the last question here because I want to get into Q&A, and we got a few minutes here to do that. And I think it's important to hear the questions that they have because you gave a lot of information out here as a group. So it was a very interesting last hour or so. And again, thank you for being a part of this today. So I'm going to ask over here, do we have any questions from the audience, either here or online? Ed?
Yeah, thank you, Mr. Chairman. So I do have a question here that I think each of the panelists might be able to provide some insights on. What is the right sharing of roles between the NRC, industry, and non-governmental organizations in helping to increase the understanding of fusion technology among both state regulators and the general public?
Anyone want to take that? You want to try? Andrew?
Yeah, I can fire off. So I think this one is key. And this is something Helion has been working on for some time. I can remember, several years ago, Helion coming in and talking with the NRC about their technology, the fuel cycle, understanding the concept. And what we've also done at Helion over the past year is actually reach out to every single agreement state and offered a presentation on our concept, similar to sort of what was given today on the overall, looking at the hazards, looking at what there is, talking about how we've been licensed in Washington State. And many of them have taken us up on that, and those that haven't, we reach back out at functions like the Organization of Agreement States, CRCPD, and other agreement state convenings. And it's something we really want to do. We don't want anyone in an agreement state to be surprised with Fusion when we come. So we've been really proactive in that regard, both interacting with the NRC, but also each of the individual agreement states, having that touch point, getting to know them, building that relationship, and explaining our technology and the hazards there.
Right. Jennifer?
I'll kind of pop this up a little bit of a level to take it not just from the regulatory. I mentioned in my opening remarks how people didn't even know what Fusion was when we first went out there. So we took it, we think there's a big responsibility on industry, government, NGOs, all the above, to help provide education on what Fusion is and what Fusion isn't, help people understand how the technology works, what the risks and hazards are and what they aren't, and how it's different from other technologies. So, we have had deep engagement with government, both at the federal level, regulatory policymakers across the board in Washington, DOE playing such a big role here too. I've done that across governments all around the world as we start to talk about this. But we take a lot of responsibility at the state and local level of doing the education, getting boots on the ground, having meetings, having open houses. One of the things we do at CFS for our Spark facility is we do a quarterly community meeting. We open the doors to our facilities and we let people tour and we tell them about what we're doing there in an open and transparent way. We talk about tritium, we talk about activated materials, and we let them ask us questions. And we have experts there because we have PhDs from IIT who show up at this, down to a local vendor who produces, burritos and wants to sell those in our kitchen. And so we view it as an incumbency to really spend a lot of time in the communities where we're going to operate. And we partnered with the local government and the state government and the federal government to try and figure out how we can do that well. And so I think there's more work to be done there. A lot of people still don't really understand Fusion and the risks and hazards. And as we build that competency, I think it gives the regulator the ability to make decisions, put them out in the public, and people understand why they made those decisions. It sort of provides cover if we're doing the education at a meaningful level across all parts of government.
So I know that going out to Washington State recently and speaking with the governor's office and people about, and after I met with Helion and ZAP and others, the need for inspectors at the state level is critical. And I was amazed really at just the forthrightness of the companies going to the state and saying, we need you to hire inspectors. We want you to bill us for these inspectors. And getting that message across to the governor. Is that happening now? Are you getting those results?
Yeah, absolutely. And, in Washington State and others, I think there was just an announcement in Tennessee recently with funding to help prepare their program where some of the other companies are doing business and as we've heard in Virginia and others. And so I think that is part of the message and why you see the Fusion companies showing up at OAS and other places to get that message out there to make sure these programs, while they have all the fundamental capabilities, there is some room for growth, certainly, and especially in resourcing and expertise and funding in that regard.
Right. So Jennifer, I'm going to come back to you for a question real quick. You talked about siting, right, and in Virginia specifically. So what are some of the things the key factors maybe that Fusion companies are looking for, and specific to you or just generally, when you consider a siting decision in a state?
Yeah, we developed, and I'm sure Helion did the same thing, and Type 1 and some other companies that have announced siting. We developed a really complex matrix of all the things that were important. And so there's always the technical aspects where we think about, the beauty of fusion is because we don't have the risk of the chain reaction and we don't have the risk of meltdown and some of the things that I think create a public concern. We feel like we can go pretty close to centers where where power is needed. So we put together this thing where we said, okay, we want it to have interconnect. We don't want to have to build a lot of infrastructure for the first one. We want it to be near the interconnect. We want it to be able to draw power, because we're going to have to do a black start, but we also want to be able to put power in the grid, and so does it have the capabilities. All these things about the site, is it capable of, easy build, things like that. But what it really came down to is we were thinking about Virginia is there social acceptance for fusion? Became one of the biggest criteria that hit the list. And that was, is the state and the county ready for this? And are they going to support this? And are they going to be hand in hand with us as we develop and do something for the first time?
Sure.
And then secondly, is the local community going to be accepting of this? And that's where I talked about these community meetings. We view NGOs as an important part of making these decisions. So some of the things that many of our companies have done is we hold meetings with the environmental NGOs and we talk this through with them. So we did a lot of work with the communities in the top 3 or 4 sites. So we met with county, local, state government, met with the agreement state regulators, and had to line all that up once we knew the physical attributes of the site worked for us.
Okay. Ed, do you have a question?
Yes, thank you, sir. So this one's for Duncan. Duncan, during your talk, you kind of paused a little bit on the transition from fusion, the change from fusion systems to fusion machines in various legislative acts. Can you elaborate a little bit on the significance of that change, please?
Yeah, when we first started the rulemaking, we did not have the Advanced Act passed. There was no statutory definition for fusion. There was no statutory definition for a fusion device or anything like that. So we developed the definition of fusion machine to incorporate kind of the machine part of it, and that machine produced byproduct material, because again, it did not exist anywhere in the statute or anywhere else in the regulations. So we had to, that's where the idea of the fusion system came from, because the most important thing is we had to say we're creating byproduct material, and that's why we can regulate. So that's really what the genesis of the fusion system definition was. With the passage of the Advanced Act, they provided a definition of fusion machine, which I described before, talks about the fusion process and what it does. And then the second part of it, by amending the byproduct material definition, says, okay, a fusion machine creates byproduct material. We didn't need to use the fusion system anymore, so we dropped it, and we now use these 2 definitions, which are in the in the statute, which are in the draft rule.
Okay, thank you. Patrick, we got about 3.5 minutes to go. I wanted to ask you, and because you've been very involved with the commission on different rulemakings and different issues, and you and NIA, so how does the use of a performance-based regulatory framework here for fusion energy align with the commission, a unanimous commission decision, as a matter of fact, on regulating fusion energy under Part 30?
Yeah, thank you for that, Chairman. So I think what it shows us is that there was a recognition by the Commission, after engaging with NRC staff, with private industry, with other external stakeholders, that near-term regulatory certainty was going to be critical, that companies were still developing their fusion technology and needed to work through the process to understand what are going to be the appropriate regulatory constraints that both enable innovation and also help ensure safety. And ultimately, looking at this Part 30 approach, it provides that kind of near-term certainty because we're leveraging decades of experience with the byproduct materials framework. Mm-hmm. And that is something, I think, as Duncan spoke about, that scales very well. Really with this recognition that as companies come and present what their machine is going to look like, what the different hazards or challenges might be, they can really work with the applicant to identify what are the controls that are going to be in place to ensure safe operation. Again, kind of building it from the ground up rather than starting with a very prescriptive regulatory framework and then trying to carve out the pieces that don't actually apply. And so I think that's something that, especially in the commission's vote, kind of looking at what they call near-term fusion machines, it provides that certainty. And again, as we start to develop experience with fusion technology, as we start to operate these machines, get to see break-even energy, we can start to have the conversation about, yeah, in the future, could regulatory systems change? Possibly, but that's a conversation that we'll need to get to in the future. And for the meantime, let's make sure that we provide that regulatory certainty so we can see companies start to innovate while we have Part 30 as kind of the appropriate guidelines to ensure public health and safety.
Thank you for that answer. We're running out of time here, looking at the timer. So it appears that we're going to have to end the panel today on commercial deployment of fusion machines. But I want to thank each of my panelists here today, Jennifer Ganton from Commonwealth Fusion Systems, Andrew Proffitt from Helion, Duncan White from the NRC, and finally Dr. White from NIA, the Nuclear Innovation Alliance, for your help. Thank you for everyone in the audience who submitted questions and for being here today. Thank you so much. You added value to the session, and I hope you enjoyed it. As a reminder, if you have follow-up questions for any of the panelists, they're going to hang around here at the front for a few minutes, so please come and grab them. And your feedback is important to us. So let us know what you thought about the RIC this year. I hope you're enjoying it. Your insights are going to be helpful to help us improve it next year and going forward. And so just follow those tabs for feedback and put your information in. And with that, I want to thank you for attending this breakout, and hope you have a great rest of the RIC. Thank you.